Okay, let's get started. Chapter 9, Nucleophilic Substitution and beta elimination. Okay, this chapter, the reactions are very easy. However, this chapter is very long and contains a lot of details about these two reactions. Okay, a lot of details. The reactions themselves are actually very easy, but contains a lot of details. So let's take a look at what are nucleophilic substitution, and also we're going to study the competing reaction of nucleophilic substitution called beta elimination. Okay, this is the chapter outline, and we'll go over every single detail from 1 through 9, and then section 10, neighboring group participation will be your reading assignment. Okay, first let's take a look. What is nucleophilic substitution? Okay, nucleophilic substitution is basically a nucleophile. Okay, we studied earlier what is a nucleophile. Nucleophile contains what? At least one lone pair electron. This nucleophile attacks an electrophile, which is a sp3 carbon, and kick away another group, because this is sp3 carbon means 4 groups already. So if this nucleophile attacks this electrophilic carbon, then something must leave, and that group that is leaving is called the leaving group. And so basically what happens is what? Is the nucleophile substituting what? The leaving group. Is that right? Let's see that, guys? And we call that reaction nucleophilic substitution. And by introducing this reaction, you see that there are 3 key components in this reaction. You need a nucleophile. Nucleophile contains at least a lone pair of electrons. So nucleophiles are all Lewis spaces, because they donate the electron to what? To what? To make the bond between the nucleophile and what? The electrophile carbon. Is that right, guys? And you have electrophile, which is the carbon that takes the lone pair electron for the bond. And finally, you have a leaving group that is displaced by the nucleophile. You can see the reaction is super easy, right? Somebody kicks this away. Somebody bonds. So basically, nucleophile bonds with the electrophilic carbon, and originally the leaving group was bonded to the electrophilic carbon is what? Is leaving. Okay, make sure you know the names of these: nucleophile, electrophile, and leaving group. The reason we call it nucleophilic substitution is because it involves a nucleophile. It involves a nucleophile. Now this is a very simple nucleophilic substitution between methyl chloride or chloromethane and hydroxide ion, OH minus. In this case, OH minus is the nucleophile, the methyl carbon is the electrophile, and the chlorine minus will be the leaving group. Of course, what happens is the OH minus substitutes the chlorine minus, so you get an alcohol. You're changing from a alkyl halide to an alcohol. What I want to show you here, you can see that in this electron map, the nucleophile and the leaving group are both what? Negatively charged. The carbon, which is the electrophile, is positively charged. So basically the nucleophile, negative charged, reacts with the positively charged electrophile, then kick away what? A negatively charged leaving group. Okay, this one show you what really happens. Okay, what really happens. Okay, nucleophile leaving groups are negatively charged with the positively charged electrophilic carbon in between. Does it make sense, guys? Okay, this is a very simple nucleophilic substitution. Now, this chart shows you if I simply use an alkyl bromide as the electrophile, or as the substrate. And if I use all kinds of nucleophile, I can build up all different types of organic compounds. For example, the one we just seen, if I use OH minus as the nucleophile, react with the alkyl bromide, I get what? Alcohol. Right, guys? Now, I'll give you a couple of minutes, take a look. If, again, the electrophile here is the same, alkyl bromide. Alkyl bromide means what? The leaving group is always Br minus. Then if I change to different types of nucleophile, including some are negatively charged, some are even neutral. Now take a look, guys. What do we get? And you will see that how simple the reaction is, but how useful that reaction is. Okay, give you a couple minutes, take a look at it. Now I'll ask you a question. Can you summarize it? What do you think nucleophilic substitution can be used for? Okay, based on this picture, based on this scheme, if I switch all kinds of nucleophile, I get all types of organic compounds. What do you think nucleophilic substitution can be used for? What do you think nucleophilic substitution can be used for? Alkylation. Not really alkylation. Alkylation means put an alkyl group on something.
Okay.
You're not putting alkyl. For example, for example, this one is switching Br with an OH, right? Not really alkylation. What do you think in a summary, like one summary? Can you tell me what do you think the uses can be? Are these reactions? Again, the reaction is super simple. Somebody kicks somebody away. Make a new bond, breaks a new old bond. But what you see from here is what? What are we doing? For example, we have changed a bromide to an alcohol, right? If I use OR minus, I change bromide to an ether. If I use SH minus, I change bromide to a what? Thiol. If I change SR minus, I change bromide to an SR, so I get a sulfite. If I use this minus, I change the bromide to this guy, I get an alkene. And if I use Cn minus, I get a cyanide, like a nitride, etc. What do you think here? Nucleophilic can be used for what? Can be used for switching functional groups. Is that right? Switching one functional group to what? To another. Think about it. If I change anything, if I can change that to a bromide, then I can use the nucleophile to what? To substitute it. Depends on what I want. Again, some nucleophiles can be negative, some nucleophile can be neutral. We'll talk about that in detail. Okay, in detail. Now, can you guys practice on your scratch paper? Show me the products of these two nucleophilic conditions. Again, we're not talking mechanism. Can you, based on this, show me the products, initial products, not in the end. Can you tell me what do we get based on these two reactions? Okay, don't look at the board. Take a look at yours to see if you. You can get the answer if you don't manage. Okay, take a look. on the board? Do you get what you get the same thing? The first reaction is what? OR serves as a nucleophile, keeps the bromine away. You get what? What is this? Ether. Good. Functional group is ether. COC is in ether, right? The second is I use ammonia, nitrogen, serves as a nucleophile, keeps the chlorine minus away. I get what? Amines, ammonium ion. Why this is a positive charge, guys? Why this nitrogen is positively charged?
Because it was neutral.
Because the nitrogen was what? Neutral. You used a lone pair to what? To make a bond. Then this has to be positive charge. That means if I want to get the final product, okay, if I want to get the final product, I need what? Somebody, another guy to what? Take a proton away. So this is the final product. Sorry. NH2. Okay, NH2. Now this is no charge after I take a proton away. Does it make sense, all of you?
Who took the proton? Was it chlorine?
Ammonia. Another one. You have a lot of them.
Okay.
Yes. If you want to do the substitute, normally I use more than one equivalent.
Okay.
Okay, more than one equivalent. No, that's right. So this, some of them serve as a base that kind of take the proton away. Does it make sense, guys? Okay, the first one, the nucleophile is negative, so you get a neutral product. The second one, the nucleophile is neutral, so you get a what? Positive intermediate. Then this somebody needs to take the proton away to give you the final product. Okay, in both cases, is what? Is the nucleophile make a bond with what? With the electrophile carbon, and then leaving of what? The leaving group. The first leaving group is Br minus. The second leaving group is what? Cl minus. Like I said, the reaction here is super easy.
So
Okay.
is the sodium goes to?
Sodium is just not, does nothing. Just stay there.
Oh.
Okay, sodium doesn't even participate in the reaction.
Okay.
Yes. The reason you have to have sodium because nobody negative thing exists alone. If I want to use methoxide, this is called methoxide, I have to use sodium methoxide because remember there's no like individual negative ions by itself. You have to add a salt. You got both negative positive. The only thing is sodium doesn't participate in the reaction. Now let's take a look at mechanism. Like I said, everything in this chapter mechanism is very easy, a lot of details. That's why we need to summarize the details of these reactions. Okay, first is the mechanism. There are two limiting mechanisms for nucleophilic substitution. These mechanisms are called SN2 and SN1. S stands for substitution, N stands for nucleophilic. The only difference is 2 and 1. I'll explain when we start the mechanism. 2 limiting means sometimes the reaction may be happening between these two mechanisms, but there are two limits regarding mechanism. 2 limits involves two distinct types of nucleophilic substitution. The difference between these two mechanisms is the timing between the bond breaking and bond forming. If you take a look at this reaction again, no matter what type of nucleophilic substitution, we're going to make a bond between what? The nucleophile and what? And the electrophile. Is that right? And then what? Break the bond between the electrophile and what? The leaving group. Is that right, guys? You're making a new bond and what? Break a new bond. Does it make sense? The difference between SN1 and SN2 is the timing. Do they happen at the same time or one happened before the other? Does it make sense, guys? Okay, let's take a look at the first one. If it still doesn't make sense, that's okay. The first limiting mechanism for nucleophilic substitution is called SN2. Again, we said S stands for what? Substitution. N stands for nucleophilic. 2 means a bimolecular reaction. Bimolecular means in the rate determining step, the transition state involves both substrates. In the rate determining steps, the transition state involves both substrates. Can anybody tell me what are the substrates we're talking about in nucleophilic substitution? What are they? What are reacting with what? In the substitution reaction, we have what? We have the nucleophile and what? And the electrophile. Is that right? And leaving group is on the electrophile basically. Is that right, guys? So that means in the rate determining step of SN2, the transition state involves the nucleophile and the electrophile. And what happens is the bond breaking of the electrophile and the leaving group happens the same time as the bond forming. Here, in this example, shows you what happened in SN2. The nucleophile use a lone pair to make a bond with the electrophile carbon. Take a look, guys. Then what? The same time, the CBr bond breaks. Again, take a look how it breaks. It's no longer radical anymore. The breaks with what? A pair of electrons with it. That's what Br leaves as what? Br minus. You see that, guys? Because these two steps happen the same time. So in the transition state, you have a partially formed bond between the nucleophile and the electrophile, and a partially broken bond between the what? The electrophile and what? What is this? The leaving group. This is the transition state. So basically, SN2 reaction happening how many steps? One step. This guy kicks this guy and this guy leaves. Then you get what? Product. This is not an intermediate. This is called what? Transition state. Okay, transition state. And this picture will help you to see what happened as SN2. This two attacks the electrophile and leaving group leaves. When the energy is the highest, we call this what? Transition state. You see that, guys? And then what? The bond keeps forming, this bond keeps breaking, you get what? Product. How many steps? One step. Why? Because we only have what? One activation energy. Does it make sense? Easy mechanism? This is called SN2. Why SN2 again, guys? SN2 means the bond forming and the bond breaking happen the same time. This word, simultaneously. And because of that, your transition state involves how many things? Two. You see that? They're both in here, right? This is the nucleophile. This is what? The electrophile. They're both involved in the transition state. And because there's only one step, so this step is what? Is the rate determining state. Because that's the only single step. That's what we call SN2. 2 means what? Again, in the rate determining step, how many species involved? 2. What are they? The nucleophile and what? The substrate, the electrophile. Okay, again, this is the energy chart. Shows you what happens. That's the transition state. One transition state, only one activation energy. You get the product. In the SN2 reaction, because the bond forming and the bond breaking happen the same time, the attack of the nucleophile is usually from the back side of the leaving group. Kick from the back. So that's why this guy can get this in the way. And that's why we say the leaving of the leaving group is assisted by the attacking of the nucleophile. Assist means what? This guy helps this guy to what? To go away. The attack of the nucleophile is usually from the back side of the leaving group, which means the leaving of the leaving group is helped, is assisted by the nucleophile. Okay, keep this in mind. We will use this topic again when we explain the stereochemistry of SN2 reaction. Does it make sense, guys? Because they happen at the same time. So if this one wants to leave, this one has to approach from the back. They cannot jump from the front. That's why otherwise they will not, they will like bump into each other. And because of that, this guy leaving of this guy is actually helped by the attacking of the nucleophile. Again, keep this in mind. We'll talk about that again when we discuss the stereochemistry of SN2. Now, after you understand what is SN2, it's easier to understand SN1. Again, S means what? Substitution. N means nucleophilic. 1 means what? In the rate determining step, there is only one species involved. And in order for that to happen, the bond break should happen first before the bond form. Think about it, guys. Put that in picture in your mind. Bond break. What bond break? Between what and what?
Carbon.
The carbon and the leaving group. Bond break first. Then what? Then the nucleophile goes what? Goes in. So somebody leave first. Leave the room first. The other one come in. Not like somebody comes in, not gonna leave at the same time. That's SN2. SN1 is what? One guy leave first. Leave you an empty room. Then what? The nucleophile comes in. Does it make sense? That's how you only evolve one single species, not two. Now think about it, guys. When the bond break, how does it break? Think about it. If CBr, let's say, when CBr breaks, Br leaves as a what? Negative. Is that right? Means Br leaves with the what? With a pair of electrons. Does this make sense, guys? Think about the previous one we see. This is SN2, of course, not SN1. But take a look. When Br leaves, Br with what? Leaves with what? With a pair of electron. Think about it. If Br leaves with a pair of electron, what does the C become? Positive. That's very good. That's what happens in SN1. In SN1 reaction, the first step, like I said, is what? Is the bond breaks. The nucleophile is not even here yet. Take a look. When the bond breaks, the Br leaves with a pair of electrons, so carbon becomes a what? Carbocation. Okay, carbon becomes a carbocation. This is called a carbocation intermediate because that's what we got from the first step, not transition state. You have this after first step. Of course, Br was a Br minus. And this step is the slow step. If the slow step means this step is the rate determining step. How many species involved, guys? Take a look. In the first step, how many guys involved? Only one. You see that, guys? What is it? The substrate, RBr. Is that right? Rx. This is the guy involved. In the rate determining step, there's only one. Nucleophile is not in here yet. That's what we call this reaction what? SN1. Now, let me ask you guys. If this step is the rate determining step, which means the slope, it tells you what? What does it tell you? In a reaction, when the reaction is slow, what does it mean? What is high?
Energy.
Activation energy is high. Is that right? The barrier is high, that's why it is slow. Okay, that's why it is slow. So this step, the activation energy is the highest. That's why it's a slow step. Of course, after you get a carbocation, the nucleophile comes in. And because carbocation is a flat structure, carbocation is sp2 hybridized. You can see that only how many bonds? 3 bonds. If it is 3 bonds, it means what? Planar. If it's planar, the nucleophile can attack from either side of the carbocation to give you the product. Okay, keep that in mind too. We'll talk about that when we talk about the stereochemistry of this reaction. SN2 attacks from where? From the back. Is that right? SN1 attacks from where? Either. Why? Because that guy is gone already. Okay, from either side. Now, in this case, the nucleophile is a what? Is a neutral molecule. Do you guys see that? This is an alcohol. If a neutral means what? After step 2, you get a what? Positive with oxygen. Oxonium ion. And that means you have a step 3. That means what? Another alcohol needs to remove a what? A proton to give you the final product. To give you the ether. Right? Does that make sense, guys? Okay, the reaction is between, let me draw the structure. Okay, sorry, I didn't draw it here. The reaction is between, okay, the reaction is between two this is the reaction between 2-bromo-2-methylpropane and methanol. Okay, first step again, take a look, guys, is what? Is the Br leaves to give you a what? Carbocation. And then this methanol attacks from where? Either side of the carbocation, because carbocation is flat, it's planar, to give you what? A oxammonium ion. Why? Because this is neutral. If it is neutral, you use a pair of electron to make a bond, then this guy has to be positive. Then the third step, of course, is somebody remove a proton. Somebody means another molecule of this guy. The oxygen is a base, it can't remove a proton. Does it make sense, guys? Questions?
Can you draw the push arrows for
First arrow first
Yes.
is this guy go away. You get a carbocation, right? Second step is, again, I mark it, this is first step. This is stepwise. Then this oxygen makes a bond with the carbocation. We get plus.
Okay.
Because this one use a pair of electrons to make a bond here. Then the third step is another alcohol takes a proton away to give you the product. Does it make sense?
Yes, thank you.
Okay, step 3. Let me write step 3. Take a look. Okay, first step, this one leaves. Second step, what? Nucleophile makes a bond with what? With the carbocation. Third step is somebody take a proton away. Again, which step is the slowest? First step. Okay, this step is called the what? Rate determining step. Why? Because delta G activation energy is what? Highest. Now take a look. Since I put it on board already, take a look at the energy chart. First, Br leaves as a Br minus to give you a carbocation. See, take a look at the activation energy. The highest, right? Second step is alcohol attacks this carbocation to give you this oxammonium ion. Energy is lower. The third step, energy is lowest, very quick. So these two steps are relatively quick. Once the carbocation is formed, these two steps is fairly quick. But involves how many steps? 3. Now, again, guys, when we talk about the energy chart, make sure you know the species. At the top of the active energy, we call this what? Transition state. We don't know what that looks like. But after we got from each step, for example, carbocation, oxammonium ion, and proton, these are called what? Intermediates. They're what we actually get from each step. These are transition state. Okay, don't get confused with transition and intermediate. Of course, that's the product. These two, the carbocation here and the oxammonium ion here, these two are intermediates. Intermediate means what? Something you got, but not the product yet. Does it make sense? These two are the mechanisms of SN reaction, nucleophilic substitution. Good? Question? No? I told you, mechanism is very easy. I promise. can see this. Push arrow is easier than what we learned before, right? Just remember, SN1, what it means. SN2, how many steps? One. Somebody comes in, somebody out at the same time. SN2, how many? I mean, SN2 is one step. SN1, how many steps? At least two. Okay, why this is three? Because the nucleophile is neutral. Otherwise, it will be only two steps. What are they? First step is what? Leaving of the leaving group give you a what? Give you what? A carbocation. Then what? Then the nucleophile what? Makes a bond with the carbocation. At least two steps. This one is three. Again, why three? Because this is neutral. Okay, at least two steps. Okay, and in the rate determining step, how many involved? Only one. That's why we call SN what? SN1. Okay, that one stands for what? In the rate determining step, only this guy is involved. Okay, only this guy is involved. Now, in SN1, because carbocation is an intermediate, you will expect rearrangement product if you can get a more stable carbocation. You guys remember that topic we talked about before? If you have a carbocation, when did we study carbocation? Which chapter?
6.
Chapter 6. When what? Alkene react with the proton. Is that right? When alkene react with proton, you get what? Carbocation. Same here. SN1, because the first step, intermediate, is a carbocation, then you may have rearrangement product if there's a chance to get a more stable carbocation. For example, this reaction. I tell you this reaction undergoes SN1. And you can even tell after we study this chapter. Okay, don't worry. But here is the electrophile. That's the leaving group. Here is the nucleophile. Normally, for substitution, where should we expect the substitute happens? Where's the location of the substitution? Here, is that right? But take a look, what do we get? Here. So that means what happened? Rearrangement happened. Okay, rearrangement happened. So let's draw the mechanism and show you these push error again. Guys, please. The reason I want to draw on board is I want you to practice drawing. Okay, let's do it together. First step. Okay, if I show you this question, ask you, okay, can you explain to me what happened in this reaction? Can you show mechanism? You should be able to do it. If this is SN1, what happens first, guys? What happens first? Leaving of what? The leaving group to give you a what? What, guys? A carbocation. Here. Is that right? Am I doing right? Am I doing right, guys? Good. Now, next step. You may wonder, okay, how do I know when there's a rearrangement? I don't know. How do I exactly tell there's a carbocation? One is based on, do we have a chance of a more stable? Number two is, take a look. You give the product already means what? It tells you what? The carbocation will be where? Here, is that right? Why? How do I know? Again, they tell you the product already. So that means this is the carbocation I got first. And I need to have a way to what? To change the carbocation to where? To here. So what happens is 1-2 shift. We have learned before, the hydrogen takes a pair of electron to shift to this guy to give you a more stable carbocation. Of course, the hydrogen is here now. Not hydrogen, actually, hydrate. Okay, hydrate, 1-2 shift. What is hydrate? Hydrate means what? The hydrogen shifts with what? With a pair of electrons. Again, the hydrogen shifts with a pair of electrons. That's why you have a carbocation here now. This is a very stable carbocation. We'll learn that in this chapter as well. This is called a benzylic carbocation. Okay, benzylic carbocation. I'll put it here. You can write it down. Okay, benzylic. Okay, tertiary benzylic carbocation. Okay, don't worry about the benzylic. Do you understand this is a tertiary carbocation, guys? Everyone? We're changing from what type of carbocation to what type? From a what? Secondary to a what? To a tertiary. First, it's more stable. You guys learned tertiary is more stable. And add on that, this is a benzylic, makes it even more stable. Okay, again, we'll talk about this word. Put it down first. I'll talk about this word when we discuss carbocation in this chapter. Okay, benzylic carbocation. And because this is more stable, this process is definitely going on. Okay, then what? Next is what? The nucleophile and what? Attacks the carbocation. We got an oxammonium ion. Again, the nucleophile is neutral, so your oxygen will be positive. And finally, what? Somebody takes the proton away, give you the product. Okay, somebody takes the proton away. Takes the proton away, give you product. Okay, you draw the product. Okay, I leave the blank for you, so guys, please, when you're done, still you can practice. Different? Because I updated last night.
Oh, okay. Okay, great.
Sorry, you can print it again, that's fine. Not much, I just rearranged so you guys more better flow. So you guys study, I study every night as well. Before you guys go to bed, I go to bed, I have to go over everything. So guys, you guys get the most updated. If you print differently, you can print it again. It's ready now. Any questions, guys? Yes.
Since for SN1 reactions,
Mhm.
it can attack from both sides, would you get, well, I think we're about to start
Racemic,
talking about.
yes. You
Okay,
get a
it's gonna be
racemic power.
racemic?
Yes.
Okay, I was.
Yes, that's what we're talking. You keep that in mind because we'll talk about stereochemistry of these reactions. We'll talk about extreme. Good question. Yes, this reaction is racemic. Okay, this is the chiral center. That's why this guy is racemic. Yes. We'll talk about that too. Don't worry.
So is that positive? What's the positive charge on now?
Here.
Yes, that.
On the oxygen.
Okay.
On the oxygen. This because the oxygen here. See, the oxygen used a lone pair to make a bond. That's why oxygen now is positive. Okay, it was neutral, right? It use a pair to make a bond. That's why it has to be positive. Okay, guys, let's review what we have studied. Substitution means what? Nucleophile takes what? Living group away. Substitute the living group. And we have two mechanisms, SN2 and SN1. In SN2, the reaction is in what? One single step. Two species are involved in the rate determining step. That's the only single step. These two species is what? Nucleophile and electrophile. The attack of the nucleophile with the electrophile happens the same time as what? The leaving of what? The leaving group, right? And because they happen the same time, attack of the nucleophile is from where? From the back side of the leaving group. Because leaving group leave in one direction, this guy attacks from the back. That's SN2. SN1 takes place in at least two steps. The first step is what? Leaving of the leaving group. Is that right? To generate a carbocation. Then the nucleophile attacks the carbocation to give you the product. In most cases. However, because you have a carbocation involved, there is a chance you will expect rearrangement product if what? If you can generate a what? More stable carbocation. Okay, more stable carbocation. And carbocation is flat, linear, planar. So attack from the nucleophile on the carbocation will be what? From either side, not from the back side. Okay, from either side. 50% chance. So your product will be receiving, like she asked, but we'll talk about when we are on that topic. Questions? No? Let's take a look at these details. We'll study a lot. This is one page. The rest of the chapter, most of them will be on this page. Okay, we're gonna study all these questions about SN1 and SN2, including the kinetics, the stereochemistry, and the factors affecting SN1 and SN2. Rearrangement, this one is covered already. Okay, I should move. This one is covered already. We just talked about it already. But these are the factors. Okay, these are the factors affecting SN1 and SN2. What are these? The substrate, the haloalkane, the leaving group, the nucleophile, and the solvent. Because solvent is very important in SN1 and SN2 reaction. So these are the topics we're going to discuss one at a time. Again, you can always refer to when you summarize. Okay, when you summarize. Again, rearrangement we'll talk already. These are the ones we summarize. When you do your own summary, this is the guideline. We'll study the whole substitution reaction. Kinetics, stereochemistry, and these factors affecting SN1 and SN2. Okay, so let's first talk about kinetics. Okay, kinetics is some topic you learn in Chem 112. Some of most of it. Means the reaction rate. In SN1 reaction, because there's only one species involved in the rate determining step, so we call the reaction first order. First order of what? First order of what, guys? Or let me ask a different way. In SN1, because only one species involved, we call that first order. Can you tell me what is involved in the rate determining step of SN1? The what?
Leaving group.
What is involved? Leaving group is part of what?
Oh.
The Rx. Is that right? What is Rx? The substrate. Is that right? Does it make sense, guys? What is R? This is Rx. Is that the Rx? This is X. That's the R. Is that right? In SN1, only one species is involved in the rate determining step. That is what? This guy. We call that Rx. Why is Rx? Because it's a halogen. Hello. So we call the reaction first order. First order means the rate law of SN1 equals to K times the concentration of Rx. Again, this is the rate law of SN1. Okay, rate law of SN1, let me put on the board. For SN1, rate equals to K times Rx. Okay, SN1. K stands for rate constant. Rx in the bracket means what? The concentration of it. How do we interpret this rate law? It means what? The rate, what is rate, guys, by the way? Rate means what? How fast or what? How slow the reaction is. The rate of SN1 is only determined by the concentration of what? The Rx. Why? Because that's the only thing involved in the rate determining step. Take a look, this is Rx. What happened here is for rate determining step? Is the leaving of the leaving group from where? From the Rx to give you what? Carbocation. Is that right? Rate determining step means what? This step determines the rate. That's what we call rate determinant. If this step determines rate, we don't care the other step because they don't determine the rate. So that means what? Again, SN1. First order means the rate is determined by what? The concentration of Rx. We can say it in a different way. If I double the concentration of Rx, the rate what? Doubles. If I triple the reaction of this one 3 times, then this one what? 3 times. But if I change the concentration of nucleophile, will the rate change? No, because the rate law doesn't even have what? Nucleophile. Does it make sense, guys? This is SN1. You need to understand the mechanism so you can understand first order. What is first order? That's first order. First order of what? First order of the Rx. We call that substrate. Does it make sense, guys? Okay, first order of what? First order of him. Does it make sense, guys? Please? Okay? Let's talk about SN2. We know SN2 involves how many species? 2, right? One guy coming and another guy leaves. So both are involved. If both are involved, the reaction order for SN2 is second order. Rate of SN2 equals to K times Rx and what? And nucleophile. You see that here? Rate equals to what? Guys, take a look. K times what? Rx times what? Nucleophile. So first order of them, first order of him, so both is how many, total is how many order? Second order. And we can explain this way. If I double the concentration of Rx, the rate what? Doubles. If I double the concentration of nucleophile, the rate doubles. If I double both, the rate will be what? 4 times. 2 times 2. Does it make sense, guys? Good. You will be asked these questions in your tests and quizzes. Please understand the rate law. Okay, because they're different. Okay, because they're different. Does it make sense? Again, SN2, because both are involved in the rate determining step. There's only one single step. There's not even 2 steps. Then the reaction is second order. First order of him, second order. You guys, at least she said she did a long time. You guys definitely learned this in Chem 112. Okay, first order of him, then the what? Second order. Second order means you double him twice. If both double 4 times. But for SN1, because only Rx is involved in rate determining step, then the rate only depends on the concentration of Rx. Again, brackets stands for concentration. Nucleophile concentration does not affect the rate of what? SN1. Because the rate determining step, there's no nucleophile involved. That's kinetics. Make sense? Okay, next, stereochemistry. Like I said, guys, you need to summarize in your book using this page. Okay, next one, we're going to talk about the stereochemistry. In SN2, we said the attack of the nucleophile is from where? From the back. If it is from back, what happened? The configuration will be inverted. If the configuration was S, after the reaction, it will become R. If the configuration is R, it becomes S. Hope you guys still remember R and S. Okay, think about an umbrella. What does invert mean? Your umbrella look like this, right? If I attack from the back, the umbrella will what? Will be what? Will be turned over. That's invert. What invert means. And there's a very famous experiment, actually, people discovered that. Okay, it's not used, whenever we talk about mechanism, people actually support these mechanisms by experiments. Okay, this is a very famous experiment by Hughes and Ingold. Okay, they use an isotope of iodine. to react with 2s2 iodooctane. This is 2s, this is S, just like here, this is S. Okay, this is S. If you guys still remember why is S? Why? Is what? Counterclockwise, the hydrogen is behind. Okay, counterclockwise. Now they use the iodo 131, this is an isotope. And they find out, in order to make this guy S to racemic, what is racemic? Half. Is that right? Okay, racemic means you what? You end up with half and half. In order to make this racemic, they only need half amount of the acetone. So in another word, the incorporation of this guy is twice as fast as, sorry, the rate of racemation, the rate make the whole thing becomes racemic, is twice the rate of incorporation of this guy. What does it mean? Think about it. If I have 2s, think about how many inversion do I need to make a racemic?
50%.
Only one. Is that right? If I have 2s, if I want to make racemic, I need what? 1s and what? 1r. So that means what? I only need to do what? One inversion. They become racemic. So that's why the rate of racemic is twice as much as what? The incorporation. That supported the idea of what? Inversion. It supported inversion. Only when you invert, you get racemic that fast. Okay, that's a very famous experiment to support the inversion of SN2. So, how do we summarize? What's the stereochemistry for SN2? Attack from the backside of the what? Leaving group. And what is the stereochemistry outcome? Inversion. Does it make sense, guys? Does it make sense?
Yes, but what if it was different nucleophile? Like,
The same, inversion. I mean, this is racemation. You use the same iodine. It's just different acid. But if you lose your nucleophile, maybe you got, no matter what you got S from R in inversion.
so it's like, it would be BR but inverted.
Quite right. Right. This is just an experiment. It shows you. If you use, for example, if you use Br minus,
Okay.
then this one will be, the Br will be in the back because you attack from the back. Okay. The same. Okay. For example, here, guys, go ahead and draw the products of these two. These are SN2. I'm telling you, there's both SN2. Can you draw the structure of the products? I'll draw it on board so you know what the inversion is. I didn't know we have a practice, so I'll draw on board so you can compare your answer with. Okay, take a look. Did you get the same answer? Again, the second one, the nucleophile is neutral, so you have to get the initial intermediate is what? Positive charge. Then somebody can take a proton away to give you the final product. Okay, you can sit closer if you want, but I don't mind.
I know we should go on the way.
Oh, you're fine, should be fine. Here. Does it make sense everywhere, guys? Inversion? Which one? This one?
Yes.
Yeah.
No, it's wedge.
It's what?
It's not dash. It's wedge. This one doesn't change.
Oh.
The reaction doesn't even have to take place over there, right? The reaction is here. That's the living group. Br is living. Methyl can never be a living group. Okay, methyl can never be a living group. Okay, we'll talk about that too, but you should know when methyl leaves as what? As C minus. There's never gonna be a living group of C minus.
So it only changes, it only inverts one of the chiral centers.
Yeah, I mean in this
Okay.
case, only inverts what? Where the reaction happens. Only invert the conversion of what? The electrophile. Okay, I should say. Because you're attacked from where? From the back side of the living group. The living group is behind, then you attack from where? From the front. That's why you get both wedge now. And also take a look, what is the nucleophile? The O is nucleophile. So COO, that's O is the nucleophile. Does it make sense?
Yeah.
All of you? Again, guys, you don't have to draw like this. I want to draw here to show you, be careful. Only show me this will be enough. Okay, that's not the product. You will never get this. I mean, you will eventually end up with this. So in your case, if I give you that question, just show me this. Does it make sense? Okay, you don't have to show me the intermediate. I need to show me that. Final product. Okay, final product. Because the base will eventually take a proton away. Okay? Next. In SN1, like we talked already, because you have a carbocation intermediate, which is planar. If it's planar, means the nucleophile can attack from either side of the plane. So theoretically, you get a mixture of R and R, R and S. 50%, 50%, because you got equal chance of it cutting from both sides. And we call the product a what? Racemic mixture. SN1, you end up with a racemic mixture. A racemic mixture. Because the carbocation is a planar sp2 hybridized carbon. Now, in reality, sometimes we do see a little more inverted product than the retention product. The reason is when the leaving group leaves, it does not go away. Sometimes they don't go fully away. They remain attracted to the carbocation, such as here in this case. We call that an ion pair. Again, when the leaving group leaves, the leaving leaves as a what? As a minus. Is that right, guys? But because the minus likes what? Plus. So initially, this guy may not go away. That means still not far away. It's still close. So that means what? This site, where the leaving group was located, is kind of like blocked. So there's a more chance of the nucleophile attack from where? From the back. So that means in reality, sometimes you will see more inverting product than this side. Or in another word, you may not see 50%, 50%. You may see 40, 60% and 40%. Why? It's because of the temporary ion pair. Blocking one side, you have more chance of attacking from another side. Does it make sense, guys? Usually carbocation is what? It's free on either side. But if the leaving group stays here for a short amount of time, then this side will be what? Will be more open. Does it make sense? So sometimes you do see a different ratio. Okay, for us, we don't need to tell. If it is SN1 racemic, but I do want to show you, in fact, sometimes we do see a partial racemization. Means they're not exactly 50%, 50%. We have more inversion product. Inversion means what? You have more from the back side, more than from the front side. It's because the ion pair. The ion pair. Does it make sense, guys? Okay, we're down for stereochemistry. Okay, next step. We're talking about one after another here. after this we talk about what? The factors affecting the reaction rate. Okay, affecting a reaction rate. The first factor is the structure of the haloalkene, the RX. Okay, the structure of the haloalkene. Regarding the structure, we'll talk about in both cases, SN1 and SN2, because there are two different reactions. So let's take a look. In SN1, how does the structure of RX affect the rate? Because SN1 involves what? Guys, carbocation. Is that right? So, the structure of RX affecting SN1 is mainly focusing on what? On how the structure of Rx determines the stability of the carbocation. Because SN1 involves what? Carbocation. Does it make sense, guys? Okay, SN1 involves carbocation. So the effect of Rx on SN1 is mainly how this guy can generate a what? More stable carbocation. Usually, tertiary Rx are most likely to react via SN1, followed by secondary. Primary Rx, you rarely see SN1 reaction. Okay, please keep everything I said here very important, because in the test, they won't ask you to repeat what I said. They will give you structures. They will ask you, hey, if I give you the structure, can you tell me this reaction go SN1 or SN2? Here is some guidelines. Tertiary is most likely to undergo what? SN1. Why, guys? Why? Because tertiary carbocation is more stable, right? We studied a long time ago. Followed by secondary. Primary, rarely you see SN1 reaction. Why? Because primary carbocation doesn't even exist. It's very unstable. Except when the primary is allylic. What is allylic, guys? We studied in chapter 8. What is allylic? When the carbon is what? Adjacent to what? A double bond. So this is allylic. If the primary carbocation is allylic, good. SN1 likes it. Why? Because allylic carbocation is very stable by what? What is it called? Resonance. Good. You can see that double bond flips. So the C plus can either be here and here. They're very stable. The charge is spread. And besides that, okay, of course, if you have allylic effect, that is primary allylic. Okay, this is the primary allylic. If you have a secondary allylic or even tertiary allylic, even good, even better. Okay. Right. Besides that, here comes the one I showed you earlier, asked you to put it down. A similar primary to allylic carbon is called benzylic, which is the primary carbon adjacent to a what? A benzene ring. And that carbocation is also very stable. It is stabilized by resonance as well. Take a look. Okay, I don't want to draw here because that's not particularly the topic for chemical theory, but I want to show you why the benzylic is stable. Remember I showed you here, asked you to put it down? Benzylic with the carbon next to benzene ring. Take a look. Why is stable? Because the carbon positive charge can be what? Can be delocalized. Okay, let me summarize again, guys. How does the structure of Rx affect SN1? Tertiary, more likely than what? Secondary. Primary, never. Okay, for your knowledge, just keep them. Primary never, except what? Allylic or what? Benzylic. They're both primary, but they're good. They're good. And this chart even shows you how relative the stability, the carbon cation is how they're really, which one is most stable, which one is least stable. This is kind of a general idea. I don't totally agree with it, but it's kind of give you an idea. Tertiary allylic and tertiary benzylic, the best. Followed by secondary allylic, secondary benzylic, and tertiary, regular tertiary. Followed by secondary and primary allylic and primary benzylic. And then the least stable ones are these two. So that means these two never have what? SN1. Why? Because the carbocation of these two is too unstable. Okay, unstable. Does it make sense, guys? Okay, that's the structure, how S and Rx decides. All right? And here you can practice, I think you can use that as a practice, we don't do it anymore. Is how can you use a push arrow to show the resonance structure of these two allylic? They're both allylic. Okay, take a look if you can show the resonance. I'll leave it to you at home. Okay, now, after we studied how Rx affect SN1, let's take a look how Rs affect SN2. SN2 does not involve what? Carbocation. Can anybody tell me again, in your own word, how does SN2 happen? Simultaneously what? Nucleophile attacks what? The electrophile, and then what? Leaving of what? The leaving group. Is that right, guys? So, if the mechanism is like this, what we just described, SN2 is mainly governed or determined by steric factors. What is steric? In a simple word, steric means how easy is the nucleophile to approach the electrophile. Or in another word, how open is the electrophile for the nucleophile to come in? That is called steric factor. Okay? Take a look at these two examples. If you still don't understand what's steric, here, this two will help you, definitely help you understand what is steric. This carbon is what type of carbon? Primary. Why? Because only one group. See that, guys? This carbon is what type of carbon? Tertiary. Tell me, if we want to do SN2, which means the nucleophile attacks from the backside, which part is more open? Here. Why? Because it's too big. You can see 3 methyl groups here. Here is only 1 methyl group. So SN2 will be faster on primary than what? Than tertiary. This is called steric factor. Okay, steric factor. Steric factor again means how easy is the nucleophile approaching the electrophile. How much blocked, how much hinders you're expecting. If it is easy to approach, rate is faster. It's hard to approach, rate is slow. Does it make sense, everyone? So here, what do we get? SN2 happens the fastest at what type of carbon? Primary. Followed by secondary. And SN2 never happens on tertiary carbon. You can put that down. Again, guys. SN2 happens the fastest on primary, followed by secondary. SN2 never happens on tertiary. Why? Because of what? Too much steric hindrance. Too much hindrance. Too much product. There's no way you can approach. SN2 never happens on tertiary carbon. It never happens on tertiary carbon. Steric hindrance not only happens on the electrophilic carbon itself, sometimes the branches on the beta carbon also will have an effect. What does beta mean? If we call the carbon of electrophile the alpha carbon, the carbon next to it is called the beta carbon. Easy? May I understand, guys? Now, previously we said SN2 only happens on what? Primary and secondary, not on what? Tertiary. Easy to understand, right? But here we want to talk about even not just the alpha carbon. The carbon next to it will also have an effect for SN2. Take a look at the picture. These four structure. What is it? This two, this two, this three. What's the difference between these? They're all what? Primary. Is that right, guys? But the difference is from left to right, there are more branches on what? On the beta carbon. And you can see how fast the reaction is. If you get more branch on the beta, the speed is what? Dropping a lot. And if you have a tertiary beta carbon, the reaction even doesn't go. It's really too slow. Okay, really slow. So that means steric hindrance not only happens for the primary carbon on the alpha carbon itself, sometimes the beta branch can also affect. If you have a heavy beta branch, SN2 is also what? Also hindered. Okay, also hindered. So that means these two guys, SN2 is very slow. This one doesn't even happen. If you have a substrate like this, SN2 won't happen. Again, guys, put these notes down. Okay, you, like I said, you won't be asked to explain by words. You will be asked by structures. SN1 prefers what? SN2 prefers what? SN2 prefers what? Primary over secondary. And never on what? Tertiary. And that's not only on alpha carbon. Sometimes the beta branch also affects SN2. If you have a heavy beta branch, SN2 will also be what? Be hindered. If you have a tertiary beta branch, like this 3 branches, SN2 doesn't happen either. Okay, SN2 doesn't. So, if you have a structure like this, no SN2. Okay, no SN2. Again, it's too crowded. Okay, it's too crowded. So here's the summary of Rx. Okay, again, I told you it's easy to understand, but please be able to interpret using structures. SN1 prefers what? Tertiary over secondary. Primary, never SN1, unless it's what? Allylic or benzylic. SN2 prefers primary, followed by secondary, never on tertiary. You can see the arrow even stuck here. There's a reason for that. I'll just show you. This sometimes isn't filtered. Right? So that's the structure of Rx. I'll move on more, then we'll stop and we'll continue next time. I'll give you some key for the quiz if you want. Next, besides the structure of their Rx, let's take a look at the leaving group. Of course, this topic is super easy to understand because leaving group always what? Leaves. No matter it's SN1 or SN2. Is that right, guys? They always leave. So that means what? If you have a good leaving group, the reaction will be what? Faster. So here is the last question. How do we know the leaving group is good? Think about leaving groups leaves as a what, guys? Anion, negative. Is that right? No matter Br minus or what minus, it's an anion. If it is a good leaving group, means the leaving group is what? More stable. If it is a good leaving group, means the leaving group is more stable. And this comes the question from chapter 4. If I want something minus to be more stable, this something minus can be regarded as a what? Where do we see B minus, something minus? How do we get a minus?
Base.
Conjugate base of a what?
Acid.
Of an acid, right? What is an acid? Think about it. HA, is that right? Let's not use why use the P minus? If I have an acid, if I get a proton away, I get what? A minus. That's A minus. So that means if I want A minus to be stable, we're talking about a weak base or strong base?
Weak.
Weak base. If we're talking about weak base, the acid will be a strong acid. So, in a word, a good leaving group is a what? The conjugate base of a what? Strong acid. Stronger the acid, better the leaving group. Okay, stronger the acid, better the leaving group. A good leaving group will be the conjugate base of a strong acid. Okay, the conjugate base of a strong acid. Here, I give you a few examples. Okay, the best leaving group are on this side. These are terrible leaving groups. And the one I put in the red box are the most commonly seen leaving group in organic chemistry. You don't see a lot. Okay, you don't see a lot. They do happen sometimes, but you don't see a lot. Especially these two, you never see. You never see. I shouldn't say you never see, but most time we don't.
What does it mean, good leaving group? Does it mean it leaves good or?
Leaves easy, quick, fast. We're talking about how these factors affect the rate. Rate means what? Whether the reaction goes fast or slow. If we have this leaving group, this reaction will more likely to go fast.
Okay.
If you have this reaction, it will likely to go slow. Slow sometimes even don't happen. Don't happen still regarded as what? Extremely slow, right? So good leaving group means the reaction will be easier to happen. Of course, we're not talking about one factor, we're talking a lot of factors. So these are one of the factors. A good leaving group means what? The conjugate base of a strong acid. Stronger acid, weaker the base. Weaker the base, but good leaving group. Because the negative charge is more stable. And these are the best leaving groups. These three and what?
How does water leave?
Hmm?
What charge does it have when it leaves?
Water leaves as water. But in order for water to leave, mostly water is the leaving group of OH. Think about it. If I have an OH, if I want OH to leave, I cannot make OH to leave as OH minus. Why? Because OH minus is a terrible leaving group. So what should I do? I pronate the OH. To make OH becomes what? OH. Let me show you here. Okay, good question. You will see that actually in some of them. If I have ROH, if I want to kick this away, somebody, the nucleophile, whatever that is, to kick this away, and this one as a leaving group, and we know OH is a what? Strong base. I mean, not strongest, but it's strong base. So leaving OH as OH minus is a terrible idea. So in order to do that, usually we add a proton first to make OH what? OH2 plus. Now when OH leaves as what? As what, guys? As water. See that? The changes the charge, OH2 becomes what? H2O now. Now we're changing a bad leaving group to a what? To a good leaving group. Water is a good leaving group. So now it means, in most cases, if you want to kick away water, you have to pronate the water first. Okay, that means you need to add acid to make the water a leaving group. Okay, you will see what, think about the lab you did. Isopentoacetate. Water is the leaving group. And take a look, if you guys write down the mechanism on the board I took, you will see that water is the leaving group. Again, these are good leaving groups. These you sometimes see, sometimes don't. These you never see. At least these three, you never see. Very rare you see these as leaving group. Why? Because they're weak strong base. They don't want to leave. Strong base, they're not stable. If they're not stable, they don't want to leave. All right, here is, we summarized first few things about substitution. Kinetics means what? what is the reaction order? Stereochemistry, are we doing retention or are we doing racemic? Structure of Rx and living group. Again, guys, these are the tiny small topics. Like I said, I won't ask you to repeat for me. I don't want to ask you to write down these factors. You will explain based on real structures, based on what you learn. To tell, hey, does this reaction go SN1 or SN2? You need to decide, because SN2 and SN2 might give you different products. Okay, that's the difficulty of this chapter. In this chapter, reaction-wise is very easy. What? Because A kicks away B. Okay, in the end, is A takes B away, but how does it happen? And a lot of factors affecting these reactions. Okay, so that's for the chapter. Quickly, let me go over the quiz. Okay, even though I haven't graded, but you probably have done it, so you know, at least you know your.
You want to stop recording?
Huh?
You want to stop?
Oh yeah, please, thank you.